Okay, so these were some of the problems at the end of the book. And one thing that I think is kind of interesting is, and the highlighted ones are the ones I'm going to go over, is they tell you like where these differential equations are used. So mechanical vibrations, that's a big highlighter. Quantum mechanics, biology, calculus of variations, that's a lot in mechanics, epidemiology, aerodynamics, so much stuff it's used in, which I think is pretty cool. So it's kind of cool that he shows like its uses. So I'm going to go through and just kind of, you're basically just categorizing these differential equations. So I'm going to go ahead and go through them. First off, for number 1, let's write it out. 5 second derivative of x with respect to time plus 4. So this is a differential equation, which is used in mechanics, it looked like. Cosine of 3t. Yeah, vibrations, electric circuits. So first off, they're just regular derivatives, not partials. So this is an ODE, an ordinary differential equation. X is your dependent variable, and t is your independent variable. That's because this is your dependent, and this is your independent. Okay. The question didn't ask for that, but it might make sense to label that. Its order, it's a second order. And that's from the highest derivative is a 2. So it's a second order. And last part, maybe the hardest part, is it linear? Okay. Well, x is our dependent variable. So if we look at the coefficients out front, we have a 5. Okay, that's fine. We have a 4, and we have a 9. So that's all linear. It can also be a function of t. It just, you can't have something like 3x squared out front. So is this linear? Yes. Okay. Number 5. We have y times 1 plus the derivative of y with respect to x squared equals some constant c. Okay, I'm going to go a little faster now because we're getting the hang of it, I think. ODE, it's a regular derivative. Number 4 right here, this would be a partial differential equation. I think they have another one right here for nuclear fission. That's a partial differential equations. But this one is in ODE. Okay, its power, or its order, is based on the power. Now, this is just a first order. Even though we're squaring this isn't a second derivative. This is our derivative squared, so it's a little different. And then is it linear? Well, no, because you're going to get y plus y dy dx squared equals c. And if you remember in the video, this coefficient, obviously that's y. That's your dependent variable. So you're going to have y times our derivative. This has to either be a constant or a function of x. And it's not. So we would say that this is non-linear. Number 9, we have x, the second derivative of y with respect to x, plus dy dx, plus xy equals 0. Okay? So this is an aerodynamic stress differential equation. So this is an ODE. There's no partial derivatives. The order, it's a second order because of the second derivative. And is it linear? So you have these terms out in front. But these are, I guess in the equation we gave, it was a of x. So it's a function of x, which is fine. So we would say that this is linear. So it's a second order linear, it's a linear second order ordinary differential equation. So there's obviously more you could practice on if you wanted. I was just going through them to give you the idea. So you kind of know how to categorize these things because based on their categories, there's like different ways to approach the problem. Okay. 14 and 15 are your just kind of word questions, I guess. So we'll do 14 and 15. The velocity at time t of a particle moving along a straight line is proportional to the fourth power of its position. So that's 14. So velocity is dx dt. It's the derivative of position with respect to time. And this is proportional, that's what that sign means, to the fourth power of x. And the proportionality just means you can multiply it by a constant. So dx dt, the velocity, is equal to kx to the fourth. And this is the differential equation. The next one, 15, says the rate of change in the temperature T of coffee at time t is proportional to the difference between the temperature M of the air at time t and the temperature of the coffee at time t. Okay, so that was 15. So the change in temperature, that's capital T, with respect to time of the coffee, is proportional to the difference between the air temperature and the coffee temperature. And again, it's the proportionality symbol means we can just put a constant and make it an equal sign. So it's C times M minus T. And this is the differential equation for the temperature of coffee. So there's more problems if you wanted to work through them, you could, but I think that kind of gets you the idea. And then we can move on to 1.2.